Hi, this is Zhang Chi, and it's my honor to present the work from weight-based to state-based fine-tuning and further memory reduction on LoRa with parallel control. This is a joint work with Zhenian Hai, Chen Jinpu, and Li Chenxiao, and we are a group of scientists from National University of Singapore. So we'll begin by looking at LoRa and its family of variants. In particular, we want to understand why LoRa and the PEFT algorithm work. Today, when you try to search online for the question why LoRa works, so the answer could be possibly this. There are some pre-trained weights here, and then we try to insert some low-rank matrices that can capture the most of the useful adaptation signals. For example, here we have A and B that's supposed to be low rank. This makes the fine-tuning parameter efficient, and it also preserves the original knowledge of the model. So following this line, there have been developed quite a lot of algorithms. For example, the LoRa and the PEFT, as well as some other algorithms like IS LoRa, Vera, and the hybrid LoRa. But the key idea is roughly the same. It's doing some weight tuning. Why the weight tuning perspective is useful? Some counterexamples exist. In fact, the idea of low-rank matrices was first proposed in a 2019 paper called Adapter. In particular, it introduced some low-rank matrices inserted between transformer layers. For example, in the figure, we can show there are two blocks of these low-rank block matrices, and then they are inserted before and after those MLP layers. So in this case, the fundamental question is are these low-rank matrices updating any of the existing metrics? The answer is probably no, because they are inserted in a sequential order instead of a parallel. So they are not modifying any of the pre-trained model. They are just plugged into the forward path. In fact, this is not the only counterexample that we can find in the PEFT community. In our 2022 paper, parameter efficient fine-tuning with control, we actually move beyond the low-rank modules completely. We use more flexible blocks like attention or residual blocks, where we still observe very strong performance. And even though there is no rank structures here. So this leads to the fundamental question of this PEFT algorithm. Are these weight fine-tuning views the only explanation or the correct explanation for the PEFT community? Now let's change our mindset a bit and jump out of the conventional weight tuning scheme. In particular, consider a classical control system where we have a system and we want to stir into a reference target. Suppose here we have some input signal and it goes through the system to generate the output signal. But the output signal may not be close to some references in some downstream tasks. So we need to build a feedback control system here. Similarly, in the PEFT algorithms, we often leave the base model untouched, and instead we insert some small modules like LoRa layers or adapters. These modules respond to the input and alter the model's output without requiring full fine-tuning. When comparing the feedback control and the PEFT, you can see these two systems are very similar to each other. The connection between control systems and fine-tuning is beyond this architectural level. So consider an LTI system and a fine-tuning neural network. So we have the dynamics of original system as well as some control variables here. You can see they are very similar to each other. Moreover, if the U equals some AR and BR, where AR and BR are both low-rank matrices, then we recover the LoRa case. So in other words, although originally seen as the weight tuning techniques, LoRa and the other PEFT algorithm has implicitly and unintentionally designed some control systems. This is a unique understanding. So for example, this is the original case where we are focusing on the weight tuning case, but this is the control system, and then we have built a link to collect these two things, and then we build a new understanding for LoRa. So LoRa is more than just doing some weight tuning. But there are some differences. First of all, the XT and the UT do not have to be the same shape in here. So for example, the XT and the UT can have a different dimension. This motivates us to think about whether W and U can have a different dimension. So in other words, U is not some completion or difference between the weight tuning. It becomes an independent variable that can perturb the state. Moreover, we do not have to stick with this linear case. We actually can use a more complex case, like a nonlinear function, to use a control. It becomes a nonlinear control in this case. Beyond this, there are other differences. So first of all, control is typically applied to the states. For example, on the right, you can see the control feedback is usually depends on the state instead of directly on the weight matrix. Moreover, the feedback control minimally disrupts the original system. In most of the cases, it keeps the original system intact, and then we try to build a new edge to the original system. The link to the feedback control actually motivates us to shift our focus from weight-based to state-based fine-tuning. For example, in the classical understanding of neural network, it is considered as multiple layers where each layer consists of multiple weight matrices. But instead, we can consider as each layer as the flowing map, where the state of the input actually flows into the graph and generates some output state. For example, here I plot some graph where the state flows through the attention block and then flows through the MLP layer. So what LoRa does is actually try to modify the flow map between two states. For example, the Q and the V block, or the Q and the V states here. But what we can do is actually more than that. We can even reroute the graph. For example, we can add a new edge from the state x1 to x6 in case x6 needs direct input from the x1. So in other words, the neural network is now considered as a directly acyclic graph, where computation is totally based on the states. Moreover, the state-based act tuning involves modifying some intermediate states with a control function. So the child state actually depends on its parent state, and we can also collect a new state to it with some new control function. Or in other words, we are free to choose any starting and ending state to tune or even to build a new edge. Now we have collected LoRa and other PEFT methods to the control systems, and we recognize that we are no longer constrained to tuning specific weights. Instead, we can select arbitrary edges, inject new pathways, or even reroute the information flow, just like designing different control systems. Let's take a moment to review the hierarchy of classical control systems. At the base, we have some LTI system. This represents the simple, elegant, and analyzable case where we add controls in parallel to the original linear time invariant system. Then we can move to the nonlinear time invariant system, a time invariance dynamics, where the original system is a nonlinear. A more widely used form is the control affine system. For example, what I show here, this is the typical control affine system. Finally, we have some fully nonlinear control system. Interestingly, the LoRa and the many PEFT algorithms actually falls into the last category. So here I plot the formulation for the LoRa algorithms where we are tuning the Q and the V block. Although it makes the tuning much more easier, theoretical analysis often becomes extremely difficult. This is actually because of the nonlinear nature of the control system. So in this paper, what we propose is actually maybe we can stop at the control affine system. So we want to make the control system decoupled from the original system. You can see from the formulation, actually the control is actually independent of the original system. What we want to do in this paper is actually similar. We want to build an edge that is independent of the original block. So what we propose in that is we build a shortcut from the X3 to the X5, or we actually can build a morph on the attention block. So our proposal is in more formula, we can keep the original formulation intact while add a new control block in parallel to this original block. The parallel nature of the control makes the analysis much more easier. For example, if we have a linear neural network here, and then for it, we can either tune each block individually with some no-rank metrics. Alternatively, we can consider all the blocks as a whole and then try to perturb with a new control matrix. And then we can show with sufficient rank, with these two algorithms have similar performance. Moreover, if the system becomes nonlinear, and then we can show in specific cases, for example, the gradient of this original function f is a singular, then if we try to put the control system into the original system, then we can only get a proper subspace. Instead, if we try to put it outside of the original block, then it always spans the whole space. This makes the formulation 2 spans a larger space than the formulation 1. The benefits of using a parallel control goes beyond the theoretical simplicity. In fact, if we want to tune a linear neural network with 2 FFN layers, then we can see if we stick with the LoRA ideas, then we need to tune the block, tune each weight metric individually. So here I plot how we tune them with the LoRA cases. In particular, we have a low-rank matrix for both FFN1 and FFN2. So when we try to analyze the memory's consumption, we can see the LoRA cases, the LoRA weights now consumes a very little part of the total memory. In particular, it only consumes 1.5% of the total memory. This is because we have the weight matrix is no rank, and the gradients and the momentums become sufficiently small. Instead, what dominates the memory consumption is the state xt0 and xt1. So why we need to store the state? The answer is that this helps us to compute the gradient with respect to the newly added LoRA weights. For example, here the AT2 is the LoRA weight, and then when we try to compute the gradient with respect to AT2, we actually need to use the xt1, the state, the forward state. So we have to keep this state in the memory for the gradients computation. In comparison, if we give up the idea of the weight-based tuning and switch to state-based tuning, we can directly build a shortcut from xt0 to xt2. This is a new edge, and we can use some no-rank metrics to build up this edge. So one of the most advantageous thing about this is actually we can release the state xt1 in our memory, so this saves the memory a lot. To validate the idea of memory saving, we conducted a series of experiments on the common sense benchmark. In particular, we select the NAMA2 7B and NAMA3 8B models, and then we compare the algorithms with the LoRA and the DORA cases. Here we tune all the 5 blocks, the QKV as well as the UD in the MLP layers. So there are 2 solutions. The one solution is we use control for the UD because the intermediate state is pretty large for the UD, and then we use the LoRA for the QKV. Alternatively, we can also use both controls for QKV and the UD. You can see from the results, the memory saving is actually significantly compared with the LoRA and the DORA case. Similarly, we also save the computation time for all the NAMA2 and NAMA3 cases. But in terms of the performance is on par with the original one or even slightly better. To summarize a bit, it saves the memory, saves the training time as well as keeping the original performance. So thanks to the memory reduction, we can shrink the batch size a bit and make the training on NAMA2 and NAMA3 possible on consumer levels NVIDIA 1390. So here I show an example where we only use 20 to 23 gigabytes to train NAMA2 and NAMA3B, 8B models. And then the performance only decreases slightly if we compare to the previous table. To summarize, the key idea of this paper is actually to show we can change our mindset and build some new understandings for why LoRA works. So in particular, the LoRA and the other PEFT algorithms are considered as weight tuning in the very beginning. But we show in this paper, the PEFT algorithms actually linked to the classical control theory, where each PEFT block is considered as a controller. Moreover, similar to the control theory, the focus of tuning can shift from weights to states. We can update any existing state edges or even build new edges to update the state. One of the examples is actually to build a control affine system where we put a parallel scheme to minimally modify the original system This allows a simpler theoretical analysis and also reduce the memory usage by skipping some of the large components. And thank you for your attention. And if you have any problem, please feel free to reach me by this email link.